Example 4.1, a nuclear power plant generates 3,000 megawatts of heat energy from nuclear reactions in the reactor's core. This energy is used to boil water and produce high-pressure steam at 300 degrees C. The steam spins a turbine, which produces an output of 1,000 megawatts of electric power. Then the steam is condensed and the water is cooled to 25 degrees C before the starting the cycle again. A, draw a scaled energy transfer diagram of the situation that includes numerical values for QH, QC, and W out. B, what is the maximum possible thermal efficiency of the power plant and the plant's actual efficiency? And then we'll go to C a little bit later. So let's just do A and B right now. So a Brayton cycle is used in power plants. So my example is for a nuclear reactor here. And so I'm going to start to set the process that goes something like this. So here is what I have right here. So on the left is I have a nuclear cycle, and on the right, you'll see a diagram that sort of shows you what it is. So here's the first thing that I want you to pay attention to. Right here, this right here, that's not bright enough. Let's go in here and make this red. This is the condenser. Sometimes the condenser is called a heat exchanger, but this is where you get the cool water. So now the cool water uses a series of pumps. You see how this is a feed pump 1, then you get to feed pump 2, and then they pump it into the boiler. So right in here is where you're seeing the boiler, which is essentially 4 and 5. So inside the boiler, you have nuclear reactions that then heat up the water. And then as they heat up the water, what you're getting here, this is sometimes called the combustion chamber in heat engines. And then what you're seeing here is that the condenser essentially has what? Here's where they eject. So what you're doing here is that this is where you're ejecting Q cold out of the system from the hot steam. And then here, in this process right here, you are now injecting Q hot into the water. And then it goes right in here. What you're going to get now is that now what you have is that you now create high temperature steam. And then they shoot that at a turbine, and then the turbine spins. So this here is where you have the turbines, and the turbines then spin, and then right in here, here is your electrical generator. And then the electrical generator, here's where you then get the work here. So the turbine then produces work out. So you see that heat comes in, part of it goes into work, part of it is ejected out. And then that's essentially what the power plant is doing. So to calculate the power plant's thermal efficiency, which is eta, and I'm going to call that of the power plant. That's the plant's thermal efficiency and its maximum efficiency. This is in the efficiency of the Carnot cycle. We need this. We know that the definition of the efficiency of anything is that it's the work out over Q hot. And sometimes it's easier to write this as the cold versus the hot. Okay, so that's going to be for the power plant, but then the maximum Carnot efficiency occurs for the temperature difference of the cold reservoir to the hot reservoir. So in order to really do this, what we have to do here is that we really have to calculate, a few things here. So when I look at this thing here, we need to calculate Q cold, Q hot, the cold temperature, and the hot temperature. Okay, so let's go do that. So the first thing I'm going to do is that we're going to look at calculating Q hot and T hot. So now look what it says here. So the words now say this. It says this power plant generates 3,000 megawatts of power. And they generate heat, but they generate 3,000 megawatts of power. And so note, so this implies here is that the power produced by the hot reservoir is not the same as Q hot. Okay, it's not the same as Q hot. And then what it says here, so note that this is all in the first sentence, right? It generates 3,000 megawatts of heat energy from nuclear reactions in the reactor's core. This energy is used to boil water and produce high pressure steam of 300 degrees C. So then if I continue to look at this thing, it then says this. This heat power, as they call it, creates a high pressure steam at 300 degrees C. So this tells me is that this is the hot reservoir. So if I look at this thing, it then tells me this, that I know that power hot is then going to be the heat ejected from this reservoir per unit time. So then that means here is that when I go to calculate this heat that's coming out, it has to be the power of the hot reservoir times my time here. So when I look at this, this number then says that I have 3,000 times 10 to the 6 joules per second, but this is generated every 1 second, which then gives us 3,000 megajoules per second, or I could call this 3,000, nope, it shouldn't be per second. It should just be joules. Or this could be 3,000 megajoules per Q hot. So now we know what the energy transferred from the reservoir to the water here. Now, if I look at T hot, you could then see that T hot is this 300 degrees Celsius, but I have to convert that into Kelvin. So I got to add 273, which then gives me 573 Kelvin is then the temperature of the hot reservoir. Okay, so this will be the temperature of the hot reservoir. So now I have these guys. So now the next thing I need to do here is that from reading the question, we need to get Q cold and T cold. So let's go look at this guy now. So if I look at the question, let's see what it says now. Look what it reads. The steam spins a turbine which produces 1,000 megawatts of electrical power. Okay, 1,000 watts of electrical power. Then the steam is condensed and the water is cooled to 25 degrees C before starting the cycle again. So now let's look at this thing here. So if I explain what I just said here, the Q hot reservoir uses its energy to spin the turbine. Which produces 1,000 megawatts of electrical power. So what you're seeing here is that it's really telling us this here, that part of Q hot goes into the work out and Q cold, and this is ejected into the condenser. So again, that Q cold is the leftover. So when I look at this, this tells me here that then the output work of the turbine is then going to be the power, which will be the work out per unit time. So then if I now solve for work out, we can then see here is that this is going to be the power out times my time, and this is going to be 1,000 joules per second times 1 second, which then gives me 1,000 times 10 to the 6, or I can write this as 1,000 megajoules for the work out. So now I know how much work has been done. Now I can use this to compute the cold here. So from the first law, we know that the cycle internal energy change must be 0, but that is Q net plus work net. And then what we do here is that tells us here is that then Q net has to be what? It has to be Q hot minus Q cold. And that has to be positive, negative network. But we redefined this to read positive work out. So then we could then solve for Q cold. And we see that Q cold is then going to equal Q hot minus the work out, which then equals 3,000 minus 1,000, which is then 2,000 megajoules for Q cold. So now we have a picture. But actually, I should wait here for a moment, because remember, the leftover steam is cooled by the condenser. The leftover steam is cooled by the condenser, and sometimes they call it the heat exchanger, to 25 degrees C. In other words, T cold is then going to be equal to 25 degrees C. Now, if I add 273 to this, then I'm going to get 298 Kelvin for T cold. So a picture now emerges for our energy transfer diagram. Our energy transfer diagram looks like this. What I'm seeing here is that I have a hot reservoir, and when I'm looking at this, the hot reservoir looks something like this. Some of the heat is going from the hot reservoir into the cold reservoir. Now, what you're going to find out here is that you could see that what's happening if I look at my cold reservoir, my hot reservoir, excuse me. Here's my hot reservoir. This hot reservoir has a hot temperature of 573 Kelvin. Now, when you're looking at this, how much heat is actually coming from the hot reservoir? Well, what you're seeing here is that the heat that's coming from the hot reservoir is then Q hot. And this Q hot, as we've already set up above here, is 3,000 megajoules. So this is 3,000 megajoules. Now, if you look at what's being ejected into the cold reservoir, you're seeing that it's 2,000, so 2/3 of this. So we're going to say here is that maybe about this amount, which I'm going to speculate is 2/3, this guy is my cold reservoir where my condenser is at. So how much heat is actually going through the condenser, into the condenser? Well, according to this is Q cold. And how much goes? This is the wasted energy of this plant. And we know that our cold temperature here is 298 Kelvin. So when you look at this thing, here's what we're seeing. You're seeing that a piece of this is now going into work. And this should be about 1/3 of that. So now this is the work out, which is now equal to 1,000 megajoules. So you're seeing how the heat engine is looking something like that. So if you were to actually look at a bar diagram, right? So a bar diagram shows then I have this amount of heat, right? And this is Q hot. And what you're seeing here is 2/3 of this is going towards the cold reservoir. And 1/3 of this is being used to do work. And that's our output work. And that's what that bar diagram is showing us here. So now that we have all our values, we could then calculate the efficiencies. So now if I come in here, I could now come in and I could now that we have all the ingredients, we can calculate the two efficiencies. Okay, so then there's the power plant efficiency. And the power plant efficiency says that eta of the power plant is then going to equal to the output work divided by Q hot, which will then be 1,000 divided by 3,000, which then gives us 0.33 or 33% efficiency for the power plant. There's another way that we could have calculated this. We could have also have gone this as 1 minus Q cold over Q hot. And if you plug this in, you get 1 minus 2,000 divided by 3,000. And you'll see here that you also get 33% for the power plant. So we now have the efficiency of the power plant. The other efficiency here, which is the maximal slash Carnot efficiency only depends on the temperatures of the reservoirs, and that's 1 minus Q cold over Q hot, and in this case, this is 1 minus 298 divided by 573, and we get a number that's 0.48 or 48%, which is the Carnot efficiency. So if I was to write this in summary, so in summary, since N Carnot is larger than N of the power plant, it does not violate the second law of thermodynamics and may be a realistic engine. In other words, it passed the first test. So now there's a third part to this question that reads like this now, which is C. Cooling water from a river flows through the condenser, the low temperature heat exchanger, at a rate of 1.2 times 10 to the 8 liters per hour. That's 30 million gallons per hour. If the river enters the condenser at 18 degrees C, what is its exit temperature? So let's think about this thing here. So the exhaust steam, that means the steam that was not used to spin the turbine, is at 300 degrees C and cooled to 25 degrees C. This is 25 degrees C by the river water. So when you think about this out loud, this means that Q cold, which is 2,000 megajoules, was ejected into the river, right? Because that's the cold reservoir. As a side note, I don't know what 2,000 megajoules are, but here's something. A conventional £2,000 TNT bomb creates about 2,200 megajoules of energy. So that 2,000 megajoules is not a small amount of money. Not money, but heat. So what we expect then, that we expect that the ejected heat Q cold to clearly change the temperature of the water. Right? We clearly expect that because of this heat, that this guy should be proportional to the change of that temperature reservoir. So now, here's what this question is asking. By how much does the temperature of the water change? That's the question that we're trying to do that. So if I was to look at sort of like a flow chart, so the process should look like this. So the first thing here is that I know that this heat has to change the thermal mass of the water, and that's going to create a temperature change. So then that means here is that when I look at the final temperature of the river water, that initial one is going to be this change in the temperature, where we already know that Q cold is 2000 megajoules and T initial is the same as T cold, which is at 18 degrees C or 298. Okay? Oh, no, this is not 298 because that was for the previous question. So what we're going to see here is that the most challenging piece is in calculating the water mass that's being heated up. The water mass being heated up. So what I'm going to do here is that the only information that they give us here is that they give us the rate of water flow, which is 1.2 times 10 to the 8 liters per hour. Okay. So that means, so what I'm going to need here is that to calculate this water mass, I'm going to need two pieces here. So this effective mass has two pieces. So the first one here is that we have the volume flow. And the volume flow says that it's the volume divided by time. So it's the volume of water divided by time. But they tell us what that is. So you could see here that this is 1.2 times 10 to the 8, and this is liters per hour. So you could see right here is that we have to convert to meters cubed per second. So if I start to do that, look at, I'm going to convert my hour now. So if I convert my hours, it turns out that my hours then are going to be what? I have 3,600 seconds in 1 hour. And I have in 1 meter cube, there are 1,000 liters. So if I look at my cancellations, you could see here is that my liters are going to cancel, and then my hours are going to cancel. So I'm now left with meters cubed per second. And if you compute that, you get 3.33 times 10 to the 4 meters cubed per second. And that's going to be our volume flow. Okay, so now I have my volume flow. So I now can convert this into to convert this into a mass, I'm going to use the mass density equation. And the mass density equation essentially says that the mass is equal to the density of water times the volume. So now all I got to do is I got to put these all guys together here. So here we go. So if I start to look at this thing, it now looks like this. So the rate of water flow is per 1 second. So that and now tells me here is that if I take my volume, and what I'm going to do here is that I'm going to multiply. So here, if I take, so let me do it this way. So then I'm going to have the mass of the water, which will be the density of the water. Now look at this. This is my volume. But now I'm going to multiply by time and divide by time. So in 1 second of time, you could then see I have my flow rate, which will then be like this. So it's going to be 10 to the 3 kilograms per meter cubed. Then I have my volume flow, which will then be 3.33 times 10 to the 4 meters cubed per second times 1 second. So you could see here is that the meters cancel out, and I get the cancellation of a second. So then when you compute this, you get a mass of 3.33 times 10 to the 4 kilograms. And that's the amount of mass of water. So if you were to convert this into pounds, that's 75,000 pounds. So now I have all of my pieces together now. So if I put them together, here I go. So now we can calculate delta T. So then I go from Q cold, it's going to be the mass of the water, the specific heat of the water times the change in temperature. And now I'm going to solve for delta T. And this gives me the mass of water times the specific heat of water into Q cold. And when I look at that, I'm going to get 3.33 times 10 to the 4 kilograms. And then the specific heat is 4190 joules per kilogram times Kelvin. And then this guy is going to be 2000 times 10 to the 6 joules. And you could see here, my cancellation is that I can cancel out the kilograms. I can cancel out the joules. And you could see that what's left here is Kelvin. So I get a value of 14.3 degrees Celsius. Now note that this is a change. I could write this as Kelvin or temperature. So when I look at this temperature change, I would say that this is definitely a dramatic increase in 75,000 pounds of water. So the final temperature of the water is then going to be T final. Is then going to be the initial temperature, which is 18 degrees C, plus the change in temperature of 14.3 degrees C, and this equals 32 degrees C from T final.